What are we made of? What is the world made of? What was the Big Bang? Deep beneath this idyllic Swiss landscape lies a unique establishment. At its heart is the largest scientific instrument ever created, and its mission? To unlock the secrets of the universe. Mankind has answered many of the most basic questions. We know why the sky is blue, that the Earth revolves around the sun, and how humans evolved. But there are still fundamental questions we have yet to answer. Questions that touch at the heart of our physical world. The Centre for European Nuclear Research, or CERN for short, is a research facility for over 7,000 scientists and academics. It aims to reveal the building blocks that form not just ourselves, but the whole universe we inhabit. The science of particle physics delves into the realms of matter and the forces that act upon it. It's research that requires amazing feats of human endeavour, with experiments taking decades to complete and performed on an epic scale. To comprehend our universe today, we must understand how it was formed, particularly during the first seconds of the Big Bang 15 billion years ago. In this programme, we'll look at the ideas that underpin research at CERN, we'll peer into the very essence of matter, and get a feel of what it's like to work at the cutting edge of human knowledge. But first, you may ask yourself, what actually is particle physics? Particle physics is the study of the subatomic world, the protons, neutrons and electrons out of which everything is made. These subatomic particles are themselves made up of even smaller phenomena, and it's these phenomena that CERN seeks to understand. By smashing electrons, neutrons and protons into each other at incredibly high energies, these constituent particles can be forced apart, and for a split second, the deepest fabric of the universe is revealed. The hope is that these experiments will lead us to the so-called theory of everything, a theory that explains everything from the smallest subatomic behaviour to the motions of the planets, stars and black holes. The key to this theory is hidden inside matter itself.
Matter is the stuff out of which everything in the universe is made. You, me, the stars, the planets, the basic building blocks of nature.
Even the ancient Greeks had some ideas that if you just divide it further and further, there might be a point at which the piece of matter that you have loses the properties, or that you can't go beyond, and they call those things atoms.
Atoms inside them have nuclei with the electrons going around the outside. Inside the nuclei, we know there are other particles called protons and neutrons. What we're trying to do here at CERN is trying to figure out what makes the universe tick. What are the rules which govern its behavior nowadays, how it came to be the way that it is, the origin of the universe, where the matter in the universe came from, where all the structures in the universe, like stars, galaxies, planets and so on, where they all originated.
Physicists and engineers at CERN use a huge 27-kilometre ring built under southeast France and neighbouring Switzerland called an accelerator to examine particles. Inside, protons and neutrons are accelerated to speeds of 300,000 kilometres per second and then smashed into each other. Particle acceleration doesn't have to be so exotic. The television you're watching right now is a kind of particle accelerator, but at CERN, the energy acting on these tiny particles is enormous. The amount of data generated during these experiments is comparable to everyone in the world talking on the phone at the same time.
So most of the CERN main site is actually in Switzerland, but most of the accelerator itself is in France. The basic reason for that is that this machine that's 27 kilometers round requires an enormous amount of power, of energy, to actually just run it, of electricity. The amount that we need is approximately the same as that given out by a small nuclear power station.
But how did CERN begin? CERN is without doubt a unique scientific establishment, not just in terms of the research carried out, but in the spirit of cooperation that founded it. Europe had been devastated by the Second World War, and as well as the effects of the war itself, Europe's scientific prestige had suffered by the emigration of influential scientists. The brain drain had begun. 11 governments agreed to set up a provisional CERN at a site near Geneva.
CERN is an international collaboration and is composed of member state countries from around Europe, as diverse as Finland, Poland, the UK, Italy.
There are 20 European countries that are members of CERN, and their governments want to study matter, they want to understand the forces of nature, and they realize that they could do it much better if they worked together rather than trying to do it individually.
The scale of the things that we're building and the cost of these things that we're building is so large that one individual country simply doesn't have the resources, both in terms of money and in terms of people, to actually do this. We have 1,800 people working on this one experiment from 31 different nations, all working together with essentially the same aim at the end of it.
There's all sorts of stories like that, of people from different cultures coming together, and they're united in their desire to understand nature, to understand the universe. And sort of questions they're asking are the same no matter what country they come from. And often they find that the different sort of approaches that you have coming from different cultures sort of complement each other. The big challenge, I think, and this is what we call the theory of everything, is to find a theory which includes quantum physics, gravity, and all the other interactions. That's the big banana.
Even science fiction writers may have trouble comprehending applications for these sort of discoveries. The ramifications for this kind of research really do know no bounds.
We don't actually know exactly what the physics that we're doing now will turn out to be useful for in the future. Now, all that I can tell you is that every advance in physics that's been made in the past hundreds of years has turned out to be useful for something.
But if you think that's all CERN is renowned for, there's another area in which the centre has changed the way we live. In late 1990, Tim Berners-Lee, a CERN computer scientist, developed what would become the World Wide Web. It was originally conceived and developed for the big high-energy physics projects, which needed to share information instantaneously between experts working in different universities and institutes all over the world. Now it has millions of academic and commercial users. Tim, together with Robert Cailleux and his team, wrote most of the communication software defining URLs, HTTP, and HTML.
I have been working with web technologies for about 11 years now. Tim Berners-Lee and I, we did the original bits in the early 90s. That was from about 1990 to about 94, where it spread inside the academic community mainly, and then began to be picked up by industry and business, and then later on the general public.
We are designing systems which assume the web. We're designing systems which operate on top of it and deal with information, and that we're no longer concerned with the worries about how we make our networks and how we define objects and how those objects interact. We can raise the level of our research and our development to a higher level.
In our case, it was quite clear that here we had hit on something which was going to go very big. I mean, that was obvious from '93 that it was going to go very big. What Tim's boss did was see this new system, buy one copy of it, and see how this could be applied with good effect in our environment, and allowed Tim to experiment with his idea using that system. We did, of course, write some browsers and some servers, but we never had the intention to keep that up and maintain it and attract clients and sell it. We could not have done that. Therefore, the very basic library of software that was a sort of example that people could use for inspiration to build on top of that, browsers and servers, that we put in the public domain. And I think also that had that not happened, then it would not have taken off.
One of the biggest things that the web has given is the leveling. It is a leveler. It allows anybody to put information up. So it's provided a level playing field, somewhere where information can be evaluated for its own value, as opposed to from where it comes from and how it's packaged.
The very important issue here is that there must be such places where there is no commercial pressure, no bottom line at the end of the month. You know, people are free to explore some avenues, and then, of course, also maybe in a number of cases fail. Right? It gives you educational value, it gives you research value, it gives you cultural value, and so on.
In part 2, we'll be finding out about how CERN will be launching the next version of the internet and searching for the Higgs boson, the holy grail of particle physics. And we'll be finding out just how you put a 1,000-ton research tool underground.